Right, so let's have a go at Unified Chemistry, the final paper in the June 2017 series. Okay, so slightly odd starter, but not too difficult once you get into it. So it's talking about some information about permafrost in the Arctic regions of the Earth. Quite interesting, but obviously you don't want to get too bogged down in that. So question 1A, the HOH bond angle in ice is about 109, but is 105 in gaseous H2O. Why? Well, if you think about it, in ice, you know that there are hydrogen bonding throughout the ice structure. So because of that hydrogen bonding, the lone pairs, which are the lone pairs on the oxygen, they're involved in those hydrogen bonds. So they become more like bonding pairs, which means the arrangement around oxygen, rather than having two bonding pairs and two lone pairs, which we normally draw it out, in ice is actually two bonding pairs and two partially bonding pairs. So that means that you don't have the lone pairs, so you don't get the higher lone pair repulsion. However, of course, you lose that when you get into gaseous H2O. You end up with two lone pairs and two bonding pairs, and as you know from AS chemistry, lone pairs repel more than bonding pairs. So part B, why are scientists concerned about the release of methane? Well, as you know, methane is one of the gases that contributes to global warming. So wants me to determine the formula of methane hydrate. Now this may freak you out a little bit, but don't let it. You've done this loads of times before. It's told you that methane is 30.4% of the mass. So that means that for water, it's got to be the rest, which is going to be 86.6%. Then do exactly what you've done before, divide by the molar mass of each, and then find the simplest ratio, and you come at 1 to 5.74. So x in this case is 5.74. Okay, so it now wants me to calculate the volume of methane in decimeters cubed released from the melting of 1 kilogram of methane hydrate. And you notice we are under non-standard conditions now, so we have to use the ideal gas equation. So first of all, let's find the number of moles of methane. Relatively straightforward to begin with. You obviously convert the 1 kilogram into grams, which is 1,000 grams. Divide by the molar mass of methane, which is 16. But you need to then times that by 13.4% because only 13.4% of that 1 kilogram is methane. And that gives you 8.375 moles of methane. Not too bad so far. Then you just bung that into the ideal gas equation, remembering to convert temperature to Kelvin, so that becomes 273 Kelvin, and that gives you 0.188 meters cubed. You have to times that by 1,000 to get it into decimeters cubed, so 188 decimeters cubed. Why do you think some industries are interested in this? Well, obviously you can use that methane as a fuel. Right, so banging on to question 2 now. Lots of information here, but this is, pretty straightforward to begin with, certainly the first part. So you're just finding the energy release. So if you work out these numbers here, here, and here, you will see that the mass of Na2O is 1.24 grams. The mass of water, or your solution, is 15.75 grams. Sorry, no, that should be 25.75 grams. Bit of a dodgy bit of writing there. And then the temperature difference is 35 degrees C. So you pop that in to your equation, which is mass of water, which is here, times specific heat capacity of water times your temperature change. Divide it all by 1,000 to convert into kilojoules, and that gives you 3.767 kilojoules. Then work out your moles of sodium oxide, which you've got. Molar mass of sodium oxide is 62. So 1.24 divided by 62 gives you 0.02. And then you pop that number over that number. And remembering it's an exothermic reaction because your temperature went up, so you need a minus sign there to give you minus 188 kilojoules per mole. So now we're going to use Hess cycle to determine the enthalpy change of 3.1. So you've noticed I put my 188 up there, which I've just figured out. And I know that this equation here is minus 57.6. So we've got to combine 3.2 and 3.3 to give me 3.1. And if you add, you notice that you need to now times 3.3 by 2 because you've got 2 HCl there but only 1 HCl there. So you need to multiply your minus 57.6 by 2. That gives you minus 115.2. Now if you add 3.2 and 3.3 together, you end up with 3.1. So you just do exactly the same to the enthalpy changes. Minus 188 minus 115.2. So let's bung that in. 115.2. That gives you your enthalpy change here to be minus 303.2 kilojoules per mole. So you notice we've already done that one on the previous page. Yippee yippee yay, and hopefully got our 6 marks. Right, so uncertainty of temperature is plus or minus 0.1 degrees C, and uncertainty in mass is 0.005. What has the greatest percentage error? So we've got to work those out. For both, you need to times your error by 2 because you took the temperature change, your temperature reading twice, and your mass reading twice. So your error for temperature is 0.2 divided by your temperature difference, which you took was 35, times by 100 gives you 0.57. Do the same for mass and you get 0.81. So the greater percentage error is mass. So the next question asks me about how I could reduce that error. Well, how I would, but I can't change the equipment. So the best way of doing it, if I can't change the equipment, I can't change that number or that number. So the only way to reduce it is to change that number and that number. So I could use a greater mass of sodium oxide, and that would obviously cause a greater temperature change here as well. So moving on to D now. Name that compound there. As you know, NO something is going to be called nitrate. What's the oxidation number of the nitrogen? Well, sodium, you know, is always +1 in a compound. Oxygen is -2, and I've got 2 of them, gives me -4. So nitrogen must be +3. So it's sodium nitrate 3. Right, so I now need to determine what's been oxidized and what's been reduced. So let's go back to this part. Sodium metal is obviously in oxidation state 0, whereas sodium oxide, the sodium is +1. So sodium has been oxidized from 0 to +1. There you go. The element reduced, well, oxygen hasn't changed. So the element reduced is going to be nitrogen. We've got nitrogen product as being 0, and it starts off with just being +3. So the change from nitrogen is +3 to 0. Right, so I'm now going to construct an equation. So I start off with NaNO2, and I react it with sodium metal, and that gives me nitrogen gas plus sodium oxide, like so. So looking at that to get it to balance, I'm obviously going to need 2 of those to get that to balance. That means I'm going to have to now have 4 Na2Os, which gives me a total of 8 over here. So to get that to balance, I need 6 there. And that should work out. Right, okay, so I've done quite a lot of working out here, which may be a little bit confusing, but I'll just talk you through it. So the first thing I have to do is find my rate equation. So the way that we're going to do that Let's just try and find okay, that should do. Let's go for yellow. Okay, so first of all, let's look at iodide first of all, because that's nice and straightforward. You can see from 1 and 2, the concentrations have stayed the same, but iodide has doubled and my rate has doubled. So the order with respect to iodide is first order. Let's look at H plus now. If I look at reactions 3 and 4 now, you can see that both peroxide and iodide have stayed the same. H plus has doubled, but the rate is the same, so it's 0 order with respect to H plus. And finally, let's look at peroxide. Looking at that arrow there, going from 1 to 3, I have doubled the concentration of peroxide. Everything else has stayed the same, but I've doubled the rate, so it's also first order respect to peroxide, which is how I get this equation. To find K, let's pick experiment number 1, put the numbers in, and you will find the answer to be 0.0200. For your units, this is obviously your rate, which is in moles per decimeter cubed per second. Concentration over here is in moles per decimeter cubed, but that's squared. So that, that's going to cancel. The square is going to cancel with that. So you end up with it being moles to the -1 decimeters cubed, seconds to the -1, which is what you've got here. Then the rate constant for this reaction is determined at different temperatures. How could we determine the activation energy? Graphically, so you plot a graph of the natural log of K versus 1 over T, and EA is equal to the gradient of the graph times minus R, which is obviously your gas constant. Okay, so we're going to power on to part B now. So first of all, I want you to look at the 2 arrows in blue, and we're going to look at these 2 reactions here and here. So why have I chosen those? Well, I've got to start with peroxide and MnO2 because that's my catalyst and my starting material. This is the only equation that starts off with MnO2. Look at the cell potential. That is 1.51 volts, and that's got to go left to right because that's got to start. This has got to go right to left, that one there, because you've got your hydrogen peroxide, which is your reactant. So looking at the arrows in blue, the electropotential number 2 goes from left to right, and electropotential number 1 goes from right to left. If you then add those 2 equations together, you get to this reaction in blue. Now we can simplify this. I've written it completely as it is, but you notice you can simplify it because you've got 2H plus there, which you can get rid of, and end up with just 2H plus there. So let's put that in there. Can I cancel it any else? No, I don't think so. So that is the first reaction that occurs. Okay. What happens next? Well, I formed in this one Mn2 plus. I've got to get rid of that. I need to reverse this electropotential here to get back to my MnO2. So this is when equation number 3 comes in, and so I've added together 2 and 3 with equation number 3 going from left to right, reversing number 2, which if you look at this red arrow here is going right to left. Add those together and you end up with this equation, which is written in red. Can you simplify it? Yes, you can. You can get rid of that 2H there to give you 2H there. You can also get rid of the waters because you've got waters on both sides of the equation like so. And that gives you your final equation. Notice how you have regenerated your MnO2 catalyst. And these numbers here are the 2 cell potentials that you would get. 0.81 volts for reaction number 1 and 0.27 volts for reaction number 2. And you've successfully reformed your catalyst and decomposed your hydrogen peroxide into oxygen gas, which is here, and water, which is here. You may be interested to may think, oh, well, where does the H plus come from? Well, you notice that you make H plus here, but you use H plus there. So if you added these two equations together, the H pluses would also cancel as well. Alright, so they've given you a slightly odd molecule here, which you wouldn't have met before, but that is likely to happen in the A2 paper. The key is this peroxy part here, which is giving you this peroxide, that OO bond there. You can draw it in a different way if you like. They are quite generous on the mark scheme, but this is the correct way of doing this. Right, so they then give you a equilibrium, so back to Kc. They want you to write Kc for this equilibrium. They've given you Kc, which is very nice of them, and they want you to calculate the moles of peroxyethanoic acid. So key thing, water is a liquid, so does not appear in the Kc expression. Everything else is aqueous, so will. So you write Kc here. You then rearrange Kc to get the concentration of peroxyethanoic acid, which is going to be equal to Kc, which is there, times your two concentrations. If you do that, you get to that being the concentration of peroxyethanoic acid. Then you need to find the number of moles in 250 centimeters cubed from here. And if you do that, you get 0.023 mole.